So this video will be all about precipitation, and we have our silver chloride reaction to look at to begin with. So our not soluble salt in equilibrium with its ions. And my first question for you is, which direction represents precipitation? Okay, hopefully you see that it is going to the left, right? The reaction going to the right is going into solution, to the left is out of solution. Precipitation is when a solid forms out of the solution. So to the left is precipitation. So then my next question is, what do you already know how to calculate to predict which way a reaction moves? The reaction quotient. So Q is back. The reaction quotient will tell you whether or not you get a precipitate. And what do you do with the reaction quotient to determine which way a reaction moves? You compare it to the equilibrium constant. So for these equilibrium expressions for insoluble salts, what we are looking at and seeing, right, Q less than KSP, based just on this, Q versus the equilibrium constant, this reaction would move to the right. The terminology that we use when it is a salt going into solution, we say that the solution is unsaturated. So it does not have as much of the salt dissolved as it possibly could, so more can dissolve. Q equals KSP. Well, this means it's at equilibrium, right? No more is going to go in solution because it's already hit the point it wants to get to. We call this solution saturated. So no more will dissolve. And Q greater than KSP. The solution is supersaturated. And a precipitate forms, and we abbreviate this as PPT. So in order to predict precipitation, well, we don't have to do too much that's different. The only different thing is making sure we can pull the right information out of the problem to put into the calculations that we need to do. So I'm going to pause here, get this problem written out, and I'll be right back. Our example problem says a solution containing lead nitrate is mixed with a sodium bromide solution. The new solution is 0.0150 molar in lead nitrate and 0.00350 molar in sodium bromide. Does a precipitate form in the new solution? So this looks a lot like the precipitation problems that we did a long time ago. However, we have actual numbers in here now. It doesn't change the first part of what we need to do, which is just figure out if any of the products are an insoluble salt. So if we take a lead nitrate solution, it has Pb2 plus and NO3 minus ions in it, and mix it with a sodium bromide solution, which would have Na plus and Br minus ions in it, and look at the possible products after, they swap partners. We have to use the solubility rules to determine if we could possibly start with a solid product. So we have all of these ions in solution. If sodium and bromide get back together, that's a soluble salt, so it doesn't count. So we should just do everything by swapping the partners and checking. So this will give us our possible products. So sodium nitrate is soluble, and lead bromide, let's get my stoichiometry right here, is insoluble. So the solubility rules will tell us this. The other way that you can check is go look at your table of KSP values, whichever one you're using. You will not find a KSP value for sodium nitrate, but you will find a KSP value for lead bromide. And the KSP for this is 4.67 times 10 to the minus 6th. So in order to determine whether or not something will precipitate, well, first we know what the identity would be. If we get one, it's lead bromide. To figure out if we get one, we have to calculate Q and compare it to the KSP. So we have the KSP, we just now need a Q value. So you need the reaction of this going into solution, or you need to be able to very easily put together the equilibrium constant expression. So I would say you need the reaction to figure out what that's going to be. So lead bromide going into solution is Pb2 plus and 2Br minus. So my equilibrium constant expression, which is also how I'm going to calculate Q, is the concentration of lead 2 plus times the concentration of Br minus squared. So I need lead 2 plus, and then I need Br minus squared. And all of this is in the problem. So a 0.015 molar lead nitrate solution, because you get one lead ion for every 1 mole of the salt, is also 0.015 molar in lead 2 plus. And then I need Br minus. So my sodium bromide solution was 0.035. And you get 1 bromide for every sodium bromide. So this was pretty nice. We didn't have to do anything to these numbers. So this Q value is 1.84 times 10 to the minus 7. So we're doing Q versus KSP. 1.84 times 10 to the minus 7 versus my KSP was 4.67 times 10 to the minus 6th. This Q value is less than my KSP. So I mixed together two solutions. I put ions together that formed an insoluble salt, but the concentration was not high enough. My Q value was not big enough for this equilibrium to move to the left. So no precipitate forms. So that's our answer. Unfortunately, we don't get a precipitate out of this solution. One of the ways that we might want to use precipitation is to do so selectively. So let's talk about selective precipitation. And what this means is I have a solution with 2 ions in it, and I want to precipitate one of them, but not the other. This is possible. You'll have to look at ion pairings to get the ion that you want out of solution, and we have to look at which one is the least soluble to figure out which one will come out first. So let's do this through an example problem. And we are going to have a solution that contains magnesium 2 plus with a concentration of 0.059 molar and calcium 2 plus at a concentration of 0.011 molar. And to this solution, right, this is solution 1, and it's just, some container, it has these 2 ions, they were presumably paired with maybe a chloride, something that would let them go into solution initially. And now I have another container with potassium hydroxide, and I'm going to add it to this first solution. So a second solution containing KOH aqueous is added to the first. Which ion precipitates first? All right, so I am telling you it is the least soluble that precipitates first. So let's figure out which one is the least soluble. So if I add potassium hydroxide to this, my potential products are magnesium hydroxide and calcium hydroxide. Magnesium hydroxide has a KSP of 2.06 times 10 to the minus 13, and calcium hydroxide has a KSP of 4.68 times 10 to the minus 6th. So we need to determine which is the least soluble. So the information that we need to work with is the molar solubility, but these 2 salts have the same stoichiometry, right? You get 1 cation and 2 anions when these go into solution, so I can directly compare the KSPs. So this is going to save us a little bit of calculation. Same stoichiometry, compare KSP. The magnesium hydroxide KSP is obviously much smaller. So magnesium hydroxide is less soluble here. So magnesium hydroxide will precipitate first. So a follow-up question, what is the minimum OH minus concentration that triggers precipitation? So precipitation begins at the exact moment when Q equals KSP. Right? This is exactly at equilibrium. In order for it to be at equilibrium, we still have to have some reactant, even though it doesn't show up in the equilibrium constant expression. That solid has to be there to have an established equilibrium with the ions that are in solution. So Q equal to KSP, my expression for calculating Q or calculating an equilibrium constant is Mg2 plus concentration times the concentration of OH minus squared. So Q equal to my KSP, which is 2.06 times 10 to the minus 13. And calculating Q, right, I want to know the OH minus concentration. So that's obviously going to be my variable here. This Mg2 plus, this is what was given at the beginning of the problem. So my solution is 0.059 molar magnesium 2 plus. So with that, OH minus squared equals 2.06 times 10 to the minus 13. I can solve for the OH minus concentration, and the precipitation will begin when this concentration is equal to 1.9 times 10 to the minus 6th molar.